US Physics Olympiad, year 2019, USAPHO. Problem A. Green Revolution. In this problem, we will investigate a simple thermodynamic model for the conversion of solar energy into wind. Consider a planet of radius r and assume that it rotates so that the same side always faces the sun. The bright side facing the sun has a constant uniform temperature T1, while the dark side has a constant uniform temperature T2. The orbit radius of the planet is R0. The sun has temperature Ts, and the radius of the sun is Rs. Assume that outer space has zero temperature and treat all objects as ideal black bodies. Question A. Find the solar power P received by the bright side of the planet. Hint: the Stefan-Boltzmann law states that the power emitted by a black body with the area A is sigma A T power 4. In order to keep both T1 and T2 constant, heat must be continually transferred from the bright side to the dark side. By viewing the two hemispheres as the two reservoirs of a reversible heat engine, work can be performed from this temperature difference, which appears in the form of wind power. For simplicity, we assume all of this power is immediately captured and stored by windmills. Question B. The equilibrium temperature ratio T2/T1 depends on the heat transfer rate between the hemispheres. Find the minimum and the maximum possible values of T2/T1. In each case, what is the wind power Pw produced? Question C. Find the power Pw in terms of P and the temperature ratio T2/T1. Question D. Estimate the maximum possible value of Pw as a function of P in one significant figure. Briefly explain how you obtain this estimate. Solution for problem A2. Question A. Find the solar power P received by the bright side of the planet. Hint: the Stefan-Boltzmann law states that the power emitted by a black body with area A is sigma A T power 4. Solution. Total power emitted by sun equal this expression, because area of sun surface equal 4 pi r sun square, and this power going uniformly from sun, so it means that on a distance r0 we have area of this sphere through which this power going is 4 pi r0 square, and only a small part of this power going through a cross-sectional area of this planet, which is pi r square. So we have to multiply this total power by this coefficient, pi r square over 4 pi r0 square, and the final answer is pi sigma rs square r square over r0 square ts power 4. So that's the answer for question A, and that was solution for question A. Question B. The equilibrium temperature ratio T2/T1 depends on the heat transfer rate between the hemispheres. Find the minimum and maximum possible values of T2 over T1. In each case, what is the wind power Pw produced? Solution. The minimum value is simply 0 because there are no heat transfers for that. It means that temperature T2 must be equal 0 and T2 over T1 equals 0. These are minimum for question B. The maximum value for T2 over T1 equal 1. It cannot be any higher by the second law of thermodynamics. In this case, there is no temperature difference, so the heat engine has zero efficiency and Pw equals 0. Power P over 2 is simply transferred from the bright side to the dark side as heat. So that was a solution for question B. Question C. Find the wind power Pw in terms of P and the temperature ratio T2 over T1. Solution. Let the heat be transferred from the bright side at rate Q1 and transferred to the dark side at rate Q2. We have Q1 equal Pw plus Q2. Then, since the two hemispheres have constant temperatures, energy balance for each gives P equal Pw plus 2 pi r square sigma multiplied by T1 power 4, and Q2 equal 2 pi r square sigma multiplied by T2 power 4. Finally, since the engine is reversible, we have Q1 over T1 equal Q2 over T2. By combining all these equations and using definition x equal T2 over T1, we have Pw equal Q1 minus Q2, or P minus 2 pi r square sigma multiplied by T1 power 4 multiplied by 1 plus x power 4. This is not yet in terms of P and x, so now we use the reversibility condition. So we have this equation for reversibility, which means that P equal this equation, and finally Pw equal 1 minus x multiplied by x power 3 over 1 plus x power 3 multiplied by P. That's answer C. That was a solution for question C. Question D. Estimate the maximum possible value for Pw as a function of P to one significant figure. Briefly explain how you obtain this estimate. Solution. Mathematically, we have to investigate behavior for this function in maximum. We see that for x going to 0, it's going to 0, and when x going to 1, it's again going to 0. First, we can just take first derivative and try to equalize it to 0. So we have this derivative equals 0, or we have this equation. We see that for x approximately equal 3 over 4, x power 4 is pretty small, and we have to figure what are roots around 3 over 4. We can investigate points 0.6, 0.7 and 0.8 and check what is the approximate. Approximate will be for x equal 0.69. For that x we have power Pw equal approximately 0.077 P. That was a solution for question D, and that was a full solution for problem A2.